Okay, this is just a quick tutorial on how to perform a linear regression using your Ti-83 calculator. Before I actually show you how to do the regression on your calculator, I need to make sure you understand a couple definitions here. I need to make sure you understand what I mean when I talk about the correlation between two variables. So basically, the correlation is the apparent relationship between two variables. Now, two variables could have different types of relationships. They could have a positive correlation, which is when as the independent variable increases, the dependent variable also increases. So if I was to draw a line of best fit that would show the trend in the data, the line of best fit would be going up to the right, which would mean that it has a positive slope. Now, not all correlations are going to be positive correlations. We could also have a negative correlation. A negative correlation would be where as the independent variable increases, the dependent variable decreases. So as x is increasing, y would be decreasing. So if I was to draw a line of best fit that would show the trend in that data, that line of best fit would have a negative slope, and that's why we call it a negative correlation. We could also make a scatter plot of the values for two variables, and we could find out that there doesn't seem to be any correlation in the data. There would be no apparent trend. Okay, no apparent trend in the data would mean that there is no correlation between the two variables. Now, not only could correlations be positive or negative, but we could also describe the strength of the correlation. We could describe the strength of the correlation as strong or weak, depending on how close together or spread out the points are on the graph. So keep in mind, we're going to be making scatter plots for two variables. We're going to have an independent variable, our x values, and a dependent variable, our y values. We're going to make a scatter plot with all the values plotted, and we're going to be able to describe the correlation as either positive or negative, and also as either strong or weak. A strong correlation would be that the points on the graph are very clustered closely together. They're not very spread out. A weak correlation would mean that they're spread out quite a bit. Okay? Now let's try and visualize this a little bit. So I've given you some scatter plots. Keep in mind the independent variable is on the x-axis, the dependent variable is on the y-axis. Now let's look at the trend in the data. So in the first graph on the left here, as the independent variable is increasing, the dependent variable is also increasing. If I was to draw a line of best fit for this data, my line of best fit would look something like this. It would be going up to the right. So it would have a positive slope, which means it would be a positive correlation between the two variables. And if you look at the data points, they're clustered fairly close to the line of best fit. They're not spread out very much, which would mean it's a strong correlation. So I would say that it is a strong positive linear correlation. If I look at the graph in the middle, as the independent variable is increasing, the dependent variable is decreasing. So the y values are going down as the x values are increasing. If I was to draw a line of best fit, my line of best fit would look something like this. That line would show the trend in the data. And that line would have a negative slope, which means I would have a negative correlation. And once again, the data points are clustered fairly closely to the line of best fit, which would make it a strong negative correlation. If I look at the last graph, there doesn't seem to be any trend in what's happening with the data points. So for this one, I would just say there's no correlation between the two variables. Okay, so what we're going to do now, I'm going to teach you how to use the Ti-83 calculator to more accurately describe the strength of the correlation between two variables. We're going to get the calculator to make a scatter plot of the data, and then after it makes the scatter plot, we're going to perform what's called a linear regression on the calculator. And it's going to give us two values, an R value, which is called the correlation coefficient, and it's going to give us an R squared value, which is the coefficient of determination. So it's going to give us an R and an R squared value, and those are going to help us accurately describe the strength of the correlation between the two variables. Okay, you've heard me say the word regression. So what does this word regression mean? Well, regression is simply the process of fitting a line or a curve to a set of data. So a line of best fit isn't always going to be most appropriate for showing the trend in data. Sometimes a curve of best fit will be more appropriate. For the example that we do on the calculator, we're going to perform a linear regression. But I just want to show you an example where it kind of demonstrates how a curve of best fit could be better suited to show the trend in the data. So if we look at this example, the same graph on the left and the right, but on the left, we've performed a linear regression, trying to use a line to show the trend in the data, and on the right, we've used a curve to try and show the trend in the data. So just simply, which type of regression seems to be a better fit? And it's probably an obvious answer that the one on the right, the curve of best fit, seems to be better. So in this case, the quadratic model, or the curve, is a better fit than is the linear model, since the curve passes through or near the majority of the data points. The points are clustered more closely to the curve than they are to the line. So the curve in this case, is a better fit. Okay. Just lastly, before I actually use the calculator to show you how to do the regression, I just want to make sure you understand what the r and the r squared values represent. So the r value is what I already told you about. This is what we call the correlation coefficient, and it's going to give us a value between -1 and +1. Okay, and it's going to be an indicator of both the strength and the direction of the relationship. So it's going to tell us whether it's positive or negative and strong or weak. A value of 0 would indicate that there's no correlation. A value of 1 would be a perfect positive correlation, and a value of -1 would be a perfect negative correlation. Now I'm going to show you the scale of how we would describe the relationship for all the values between -1 and +1. So let's just look at the right segment of this scale for now. We're going to look at the positive linear correlation side. So all values between 0 and 1 indicate that there is a positive linear correlation. And then depending on what the actual value is between 0 and 1, that'll tell us the strength of the positive linear correlation. So the first third of the values between 0 and 1, so from 0 to 0.33, we have a weak positive linear correlation. The middle third of the values, from 0.33 to 0.67, we have a moderate positive linear correlation. And then the highest third of values between 0 and 1, so from 0.67 to 1, we have a strong positive linear correlation. And the same thing applies on the negative side of the spectrum. So the negative side of the spectrum just implies that we have a negative linear correlation. So negative numbers don't necessarily mean like a weaker correlation. It just means that the direction or the slope of the line of best fit would be down to the right, meaning the slope would be negative. Okay? So if we have values between 0 and -0.3, we have a weak negative linear correlation. Between -0.33 and -0.67 is moderate, and between -0.67 and -1, we have a strong negative linear correlation. So let's visualize this a little bit, comparing a scatter plot to what the corresponding R value would be. So if we look at this graph here on the left, we'll notice that the line of best fit is going down to the right, so it has a negative slope. Okay, which means that we would have a negative correlation, and the data points are, they're spread out a little bit, but not too much, but they're not clustered really closely to the line either. So it says here that the R value for this set of data is -0.5. So that value of -0.5 would imply that we have a moderate negative linear correlation. If we look at the graph in the middle, there doesn't seem to be any correlation in the data, and that's why the R value is 0. That's implying that there is no correlation in the data. And if we look at the last graph on the right here, all of the data points lie exactly on the line of best fit, and the line of best fit is going up to the right, which means we have a positive slope. So that indicates a perfect positive linear correlation, which is why the R value is 1. The R value is +1 because it is a positive slope of the line of best fit, which means there's a positive correlation. And because they all lie exactly on the line of best fit, they're all clustered really close together. That's why we have a very strong positive linear correlation. Okay, now let's look at the other value the calculator is going to give us. It's going to give us an R squared value. So it's going to take the correlation coefficient, and it's going to square that value. So we're no longer going to be able to have negative numbers. We're going to have numbers between 0 and +1. So it's no longer going to tell us about the direction of the relationship. It's just going to give us another value that will help us describe the strength of the relationship between the two variables. And in fact, what we're going to get, so let's say we got an R squared value of 0.44. What that actually means is that 44% of the variation in our dependent variable is due to the variation in our independent variable. So it's going to give us the percentage of variation in y that we can say is due to the variation in x. And keep in mind what you're going to have to do. You're going to have to change your R squared value to a percent by multiplying by 100 to figure out what percent of the variation in y is due to the variation in x. Okay. One important more distinction we have to make before we actually use the calculator to do the regression is that we have to make sure you understand that the correlation coefficient, the R value, is a measure of the linearity of the data. So we can only use it when a straight line fits the data. However, the r-squared value is defined in such a way that it applies to any regression curve. So you can use your r-squared value to help you describe the relationship between two variables no matter what type of regression you do. But the r value is only useful when we do a linear regression. So we're going to perform a linear regression for this example right here. So I'm finally going to show you how to actually use the calculator to perform the regression to get the equation of your line of best fit, your r value, and your r-squared value. So here's the example. One of the science classes is growing a bean plant. The height of the plant is measured every few days. The results are randomly collected in the table below. So I've got my table of values. I've got my independent variable, the day, and my dependent variable, the height of the plant. Now, to perform the regression, what you're going to have to do, so you have your calculator, most likely you're going to have some data already stored in your calculator from previous questions that you've done. So first thing you have to do is clear that data. To clear the data, you have to press second plus 712. And what that's going to do, it's going to clear all your lists, clear all your memory, so you can start fresh with this example. I'm not going to press those buttons because I already have this data entered and I don't want it to erase. Okay. So after you've cleared your memory, so you press second, then plus, then 712. Next thing that you're going to do is you're going to want to input your data into your calculator. So what we're going to do, your independent variable is going to be put into the L1 list. To bring that list up, you need to press Stat and then Edit. So number 1 is Edit. You're going to see lists. I've already entered all of my independent variable values into L1 and all of my Y values into L2. That's what you need to do. So take a moment now, pause the video, and do that. Okay, now that you have all of the data entered into the calculator, next thing you want to do is actually bring up the scatter plot of the data. In order to bring up the scatter plot, you might think, okay, hit graph. If we hit graph though, you're not going to see anything, and that's because you haven't turned the stat plot on. So what you need to do is turn that on by pressing second and then y equals. And then you'll notice that plot 1 is off. You need to turn that on. So press enter and then highlight the on button and press enter again. So now on is highlighted. So that tells you that stat plot 1 is now on. And the default type of graph that it's going to give you is a scatter plot. So if you go down to type, scatter plot should already be selected. And the default list for your independent variable should be L1, and the default list for your dependent variable should be L2. So you won't have to change that at all. Now you should be able to hit graph, and you'll see something. You'll see some dots on there, but you'll notice it's not zoomed in properly on your data. So to do that, what you have to do is press zoom, and then number 9 will zoom in on your data that you have entered, zoom stat. So we'll press number 9. And now we'll have all of the data that we have entered, all the points that represent our data. Okay, so we haven't gotten our R or R squared values yet, but just based on the visual representation of this data, how will we describe the correlation of this data? Well, it seems that the data is going up to the right. So if I was to draw a line of best fit, it would have a positive slope. So there's a positive correlation here, okay? As the independent variable is increasing, the dependent variable is also increasing. So as the number of days is increasing, the height of the plant is increasing. And that makes sense. So let's describe the correlation here. So there's a strong positive linear correlation, there seems to be. Now let's actually perform the linear regression so we can more accurately describe the strength of this correlation. So to perform the linear regression, what you need to do is press Stat, go over to Calc, and then linear regression is number 4. Now you press enter on that, and before you press anything else, we also need to tell our calculator what variables do we want to perform the linear regression for. Well, we've put our independent variable in L1, so we need to press L1, which is above 1, so second 1. And then we put our dependent variable in L2, so we need to press comma, second, and then the number 2 to get L2. Now, we also want the equation of the line of best fit to be graphed on our scatter plot as well. So we need to tell our calculator to store the equation of the line of best fit in Y1. So to do that, what we have to do is press comma, vars, go over to Y vars, and then the function, number 1, Y1, which is number 1. So good. We're going to perform a linear regression of L1 and L2. So my independent variable is in L1, my dependent variable is in L2, and it'll put the equation of the line of best fit in Y1 so that it'll appear on my scatter plot. Now I can press enter. So linear regression of L1, comma L2, comma Y1, enter, and it'll give you all the values that you'll need to describe the correlation of the variables. So it's given us the r value, the r squared value, and it's also given these two values a and b. And what those values are the values that you'll need to write the equation of your line of best fit. The a value is the slope, and the b value is your y-intercept. And just plug that into y equals ax plus b. So y equals 0.938x plus 1.001. So what is the equation of the line of best fit? We'll just plug those values into y equals ax plus b, and that gives you the equation of your line of best fit. So there's the equation there. Y equals 0.9383x plus 1.001. Next thing we want to do is we want to look at the r and the r squared values and actually state what those tell us about the correlation between the variables. So what is the correlation coefficient? Make sure you understand that the correlation coefficient is the r value. Okay, so the r value is 0.969. So there's my correlation coefficient. And what does that mean? If you look back to this slide here, it shows us what all the r values mean. An r value between 0.67 and 1, which is where our r value falls, indicates a strong positive linear correlation. So let's go back and write that description in. So this r value here indicates a strong positive linear correlation. It's very close to the value of positive 1, which means it's a very strong positive linear correlation. Now let's get the coefficient of determination. And make sure you remember that the coefficient of determination is the r squared value. So basically the r value has been squared. And we have 0.939. Now what does that value mean? Remember that you have to multiply that value by 100 to get the percentage of the variation in y that is due to the variation in x. And you have to remember that what our x and y variables are. Our y variable is height, and our x variable is days. So what it tells us is what percentage of the variation in height is due to the variation in the number of days. So let's go back and write that out. It tells us that 93.9% of the variation in plant height is due to the variation in the number of days. So how confident are we to the answer that was in part D? Our answer to part D was that there was a strong positive linear correlation. So based on our r and r squared values, we've verified that there is a very strong positive linear correlation. The r value is very close to 1, which tells us it's a strong positive linear correlation. And the r squared value tells us what percentage of the variation in the plant's height was due to the variation in the number of days, and it was a very high percentage. So we can be very confident in our answer to part D. Next thing you want to be able to do is actually use the equation of your line of best fit. So we want to be able to use this equation here. We want to be able to use that equation to make estimations for our data. So use the equation in part D to predict the height of the bean plant at 20 days. Or it should say for part F, in part F. To predict the height of the bean plant at 20 days. So keep in mind days is the independent variable, so that's our x value. So all we have to do is plug the value of 20 in for x into our equation of our line of best fit. And then we can solve for what height we would expect to have. And we would expect to have a height of 20 centimeters. Okay, the next thing I want you to be able to do with your calculator is be able to determine the residual values. Basically, residual values are good for analyzing linear relationships as well, okay? So not only are the r and the r squared values good, the correlation coefficient and coefficient of determination, but we also want to be able to know what residual values mean as well, okay? A residual value, most simply put, right here, is the vertical distance between a data point and the line of best fit. So if the regression model is a good fit, all the points would be very close to the line of best fit, which would mean we would have very small residual values. And there should be no noticeable pattern. If we have large residual values, that would mean the data points are far away from the line of best fit, which means that maybe our regression wasn't a good model at all. Okay, so if we look at our scatter plot that we just did, if I bring up the graph, my line of best fit will now be graphed, and you'll notice all the data points are fairly close to the line of best fit, so I would have very small residual values. Let me show you how to actually calculate the residual values. So you can actually have numerical values that we can analyze. So what we're basically doing, we're finding the distance between the line of best fit and our actual data point. So to calculate that, what we need to do is take our actual y value for a certain piece of data and then subtract what y value we would expect for the corresponding value of x. So if I actually do an example, it'll probably help you visualize or understand better how to use this formula here. I'm also going to show you how to use the Ti-83 to get your residual values. So, for example, here's our data table. It told us that on day 0, the height of the plant was 1. It was actually 1. Okay? If we look back at our scatter plot, you should be able to see that point in the bottom left corner there. There's the data point. Okay? And it looks like it's almost on top of the line of best fit, if not exactly on top. But we'll calculate that right now. We'll see how far that point actually is from the line of best fit. So in order to do that, what we need to do is we need to figure out, okay, using the equation of the line of best fit, what height would we expect on day 0? So the equation of our line of best fit, let me just find that again. It was y equals negative, or sorry, 0.9383 is y equals 0.9383 x plus 1.0011. I think that might be right. 001. Yes, okay, good. That's the equation of the line of best fit. Now, let's figure out, okay, so on day 0, the height was actually 1, but according to our line of best fit, what height would we expect? Keep in mind, y is the height. What height would we expect? So y is the height on day 0 when our x value is 0. So all we have to do is plug in 0 for x. So 0.9383 times 0 plus 1.0011. And if we solve that, we would get a height of 1.0011. Okay? So according to the line of best fit, the height we would actually expect for the plant on day 0 would be 1.0011. Now the residual value is basically the difference between the actual height and the expected height, or the calculated value using the line of best fit. So what's the difference between 1 and 1.0011? We'll just do 1 minus 1.0011, and we would get negative 0.0011. So that's the residual value. Now we don't want to have to do that for every data point, so let me show you how to use your calculator. So we're not going to have to figure out the calculated value for the rest of these. I'm going to show you how to use your calculator to get all of these values. So, on your calculator, what you need to do to get the residual values is go back into your lists. So go Stat, Edit, and go over to L3. We're going to get our calculator to put all of the residual values into L3. So after you've scrolled over to L3, hit up, and then enter. So hit up so that L3 is highlighted, then press enter so that your cursor is flashing at the bottom of the screen beside L3 equals. Now, what you need to do is you need to tell your calculator to put the residual values there. The residual values are located in the list function. So you need to press second, stat, because list is above stat, and then on your calculator, number 7 will probably be residuals, but on my calculator, it's number 1. So hit number 7 to get residuals. And then it should be at the bottom of your screen there, and then press enter, and your calculator will input all of the residual values into your calculator for you. And then you can just copy them onto your list there. And you'll notice the first residual value is what we had calculated, negative 0.001, and that's what we had calculated as well. So you can copy all of those onto your list, and then you've got all your residual values. So I'll just copy a couple down. The next one was 1.6, roughly. And then the one after that was negative 1.5, and so on. I won't copy them all down. But basically, you have to understand what these residual values mean. This residual value of 1.6 means that if we look back at our scatter plot, let's bring up the graph. If we look back at the scatter plot, what does that residual value of 1.6 mean? Well, it means, okay, so on day 10, the actual height was 12, okay? But the residual value of 1.6 means our data point is actually 1.6 units higher than our line of best fit, okay? So the data point, or the height of the bean plant on day 10, is actually 1.6 centimeters higher than what we would expect based on our line of best fit. If we look at the next residual value, negative 1.5, it means that on day 8, the height of the plant was 7. This residual value of negative 1.5 tells us that a height of 7, okay, is 1.5 centimeters lower than the height we would expect from our line of best fit. So it's 1.5 centimeters below our line of best fit. If you want, we can actually put those residual values onto our graph here. To do that, all you have to do is turn another stat plot on. So stat plot, let's turn number 2 on. We'll turn it on, and then our y list will want the residual values on the y list. So second stat, and put the residual values there, and then hit graph, and then your residual values will show up at the bottom there. It's probably useful to make them appear as different dots. So I'm going to go back to stat plot 2 and change the dot type to those crosses so that we can distinguish the difference between the residual values and the actual data points. And the residual values are at the bottom of the screen there. And this is a zoomed in version of that. So this might help you better understand what residual values are. So this data point here, if we look at that data point there, it's below the line of best fit. So its corresponding residual value will be below the x-axis. And notice the distance between this data point and the line of best fit, that distance there, should be equivalent to the distance of this data point between that data point and the x-axis. Okay? And notice this data point is above the line of best fit by that much, so its corresponding residual value should be above the x-axis by that much. Okay? The residual values tell you the vertical distance between a point and the line of best fit. So this residual value tells us the corresponding point should be below the line of best fit, and if we look up, that's the case. And I think that's all I'm going to show you in this video. If you want to, I'm going to skip over a couple things here. If you want to, here's another example that you could try performing a linear regression for. And so if you want, you can pause the video now. I'll make this a little bit bigger so you can see it. You can input all of this data into your calculator. So you could first press second plus 712 to clear all your lists, and then put this data. So put your independent variable into L1, put your dependent variable into L2, and perform a linear regression. Get your R value, your R squared value, and use those values to describe the correlation. So pause the video here, put those in, and I'll put up the answers in a second. Okay, so now you've put them in. Hopefully you've performed your linear regression. The equation of linear regression should be that. The correlation coefficient would be 0.9, which also indicates a strong positive linear correlation. And the coefficient of determination would be 0.8241, which indicates an 82.41% of the variation of the points scored is due to the variation of minutes played. Also, you can try and calculate your residual values using the calculator. And those are the values that you should have got there. Hopefully you can see those. I'll zoom in a little bit. I'll try to. There we go. Hopefully you can see those. And I think that's all I'll show you for that. So hopefully you've tried a couple examples, and hopefully you're confident performing a linear regression using your calculator now. And just let me know if you have any questions.